This is a lecture now on phase lines and equilibrium solutions as they're represented on phase lines. And this is the first look we have at dynamical behavior for the differential equations. For phase lines, we're going to consider the following. They're going to be the autonomous differential equations, because if you remember, the isoclines were very simple. For an autonomous differential equation, let me get the pen. dy by dt is some function of y only. Now in this case, what are the isoclines? The isoclines are all horizontal lines. There's no t dependence, so they're horizontal lines. In particular, the nullclines are, these are the isoclines with, all right, let's write this again for review. An isocline, the derivative is constant along an isocline. For a nullcline, c is equal to 0. The derivative is 0. For these autonomous differential equations, the nullclines are also equilibrium solutions. Now, what the nullclines do is sort of carve up the region in the yt plane into different regions. And in each region that's between nullclines, all the slopes have the same sign. They're all positive, they're all negative. The flow, you could say, is similar between the nullclines. Now that holds for both autonomous and non-autonomous equations. But for the autonomous equations, there is no time dependence, so why write out that whole yt plane? All that information can be summarized in one vertical line, and that vertical line is called the phase line. So again, this applies only to the autonomous differential equations. And it's called a phase line because it is a first order equation. In the next chapter, we're going to have phase planes because these are second order equations that we're going to be studying in chapter 2. But here's chapter 1, first order equations, phase line. So here's a picture of what we were talking about in the previous lecture on the direction fields. This is what we have. This is from the previous lecture. Right, and in this case we have 3 equilibrium solutions. I had to write them in because the computer couldn't do it so well. One's at 3. Here's another equilibrium at 1.5. Here's another one at 0. Now they carve this yt plane into strips, and each of these strips, the flow is similar, so the sign of the derivatives, the signs of these tangents, are the same. The sign is. So below 0, they're all positive. All right, between 0 and 1.5, in this case, they're negative. Between 1.5 and 3, they're positive again, and here they're negative again. Well, we've written this, say all this information is duplicated as you move across in t, and so here is the phase line that summarizes all of this information. The equilibrium solutions are the dots, and if it's negative, if the tangents are negative, that's represented by one down arrow. If they're positive, it's represented by an up arrow. Now this drawing the phase line is fairly simple. What we're going to look at now for the rest of this lecture are these equilibrium values and what's called their stability. Equilibrium solutions, these equilibrium values are classified either as stable, unstable, or semi-stable. There's another name for the stable, and it's called the sink, and the unstable is also called a source. Unfortunately, for those of us who are glancers rather than careful readers, there's a lot of S's here, so you have to kind of move over to the second letter. I tend to just use the word stable, unstable, semi-stable, and then add sink and source in later. Okay, so here is a classical mental image that's presented for what stability means. The idea is that you have some kind of experiment or some kind of device situation, and the situation is in stable mode. It's stable, and then something comes along and bumps it or disrupts it slightly. if that disruption causes, it will cause a change, and if that change is immediately or asymptotically return to the stable situation, return to the equilibrium situation, it's called stable. Let me repeat that. You have um, you have something in an equilibrium situation. It is bumped off of equilibrium. If it returns, even asymptotically returns to equilibrium, that equilibrium is called stable. If instead, when you bump it, it moves off of equilibrium and then flies away, never to return again, that's an unstable equilibrium. If it falls in one direction and it would return, but in the other direction would fall away, that's called semi-stable. So here's a graphical picture of that using a marble on sort of a curved surface. This is a stable marble right here. You see if it got disrupted, if that marble moved up here a little bit, it's going to go right back down. If it moved in this direction, got disrupted over here, it's going to come back. This one is unstable. So if you knocked it off of this equilibrium position, it's going to go away here, or it's going to go away here. It's not coming back up to that peak. And then the red one, of course, is semi-stable. If we go in this direction, it's going to turn around and come back. If we go in this direction, it's going to fall away from that location. I know we're talking about solutions of differential equations, and there's a characteristic way that these solutions look when they're stable or when they're unstable or semi-stable. This horizontal line here is the equilibrium value. If this equilibrium is stable, as shown here, then the solutions converge to it in forward time. That means as time goes on here, all these solutions are coming down into it. And of course, this is asymptotically stable. And that's fine. It's still considered stable. They're never going to reach it, but they're converging on it. So this is a stable equilibrium. Now this one is unstable. Well, here's the equilibrium value again. This horizontal line here, because we're only talking about these autonomous equations, and so the isoclines, in particular the nullclines, are horizontal lines. The others are solution curves. They're not isoclines. Okay, in this case, it's pretty much the opposite of what we had in the previous graph. And as time marches on, these solutions are moving away from the equilibrium. If you look backwards, they're converging to it in backward time, but in forward time, they're moving away from it. So this is called an unstable equilibrium. Now there's several methods to determine whether the equilibrium solution is stable or unstable or semi-stable. And in one case, we can just look at the phase. If we draw a phase line, we can see it immediately. Oops. Okay. So if we remember for the stable situation, say if that was equilibrium, then these solutions are converging onto it. So here would be the equilibrium on the phase line would be this dot. These have to be coming, the ones above it are descending on it, so you see the negative arrow here, negative going arrow here, and you see this other arrow in this direction. Okay, this is a stable equilibrium, or it's a sink, when the arrows are pointing at it. The word sink sort of has a negative connotation, but you can think of things going down the sink, the arrows pointing, all the dishwater is flowing, hopefully, down the sink. Okay, here's an unstable one. Remember, this is equilibrium, it's unstable, the solution curves are flying away from it. So, I'm sorry, negative. So in this case, they're going away from it, so these arrows going up, away from the equilibrium, and pointing down when it's below it, because it's going away from the equilibrium. For source, you can think of it as something that's spewing things forth, and that's why you might call it a source. If for semi-stable, you have one approach, like this one would be negative, slopes above it, and negative slopes below it. So in this case, here's the equilibrium value. These look like they're coming down on it, and these are going away from it. Or it could be the opposite direction. So again, this is stable when the arrows are pointing toward the node. They're unstable when the arrows are pointing away from the node, and they're semi-stable when they're, looks like they're pointing through the node, you could say. So that's the information right from the phase line. Now, if you don't want to draw the phase line, or essentially draw the solutions, there's three methods. Actually, the first method is essentially the method of the phase lines, but there are three methods for determining the direction of the arrows and then the stability of these equilibrium solutions. One method, you use the signs in those regions around, above, and below the equilibrium value. So in that case, you're essentially drawing the phase line. The second method, you use a graph of the first derivative. And the second method, you use the slope of the graph at the equilibrium points. So I'll show all of those three methods now. So here's the first derivative test, or that first method. You have an equation. For example, here's an equation from the textbook. And you need to find first the equilibrium values. So to find the equilibrium values, you set this equal to 0. Oops. You set this equal to 0, and you find the values are, there's an equilibrium when y equals 0, when y equals n, and when y equals m. And here we have m less than n, so this is, put them in order here. Okay. Those values divide the y-axis into different regions, those intervals between these equilibrium values, and you evaluate this derivative between those values. So starting at minus infinity to 0, because that would be the lowest region, you find that it's positive. How do you do it? You take something like -1 and put it through this equation and see if the result is positive or negative. Then you have to go from 0 to m. You'd have to put y equals, for example, here if you put y equals -1 for a test, here you could put y equals m over 2, run that through the equation and see whether the result of dy by dt is positive or negative. This is the sign of the slope, dy by dt. And then here, figure out some number between there, halfway between, and here you could put something greater than n. Okay, and then you get those out. So you have to find a number in this region, put the number back in, or value back into the differential equation, find out whether it's positive, or negative. And then you can go ahead and draw the phase line. You don't have to draw the solution curves, but I drew the solution curves here too. This is just a case where I gave some values to m and n. So here's one equilibrium at 0, shown as a dot. M equal 3 was the equilibrium. Another was n. In this case, n was 5. And then looking at the signs, you have the positive sign here. Let me write that in. So you get your positive signs here, negative signs here. Positive and negative. Okay, these arrows are converging on this node of n, this equilibrium value of n, it's stable. The arrows are converging on this equilibrium value of 0, it's stable. For the equilibrium value of m, you see the arrows are pointing away, they're unstable. Remember, the arrows will not change direction. In this region, they're either going to be positive or negative. They can't change direction. If you remember, that was because of continuity. If it's going positive, to go negative, the slope has to go to 0. But the slope can't go to 0 in this region. It can only be at 0 at n, m, and 0 at the equilibrium values. Now the next test is the first derivative graph. And if you suffer from or enjoy any kind of dyslexia, which I take as a sign of genius, obviously because I have plenty of it, you've got to really adjust your thinking. We're used to drawing the graph of a solution, and then we're used to eyeballing along it the slope and calling that the derivative. Here we're going to graph the derivative. We're graphing dy by dt, and we're graphing it against y. Now that's kind of strange because we're thinking all the time we're looking for a solution y of t, but we're not looking, this is not y as a function of time, it's just values of y. So we're looking just at values of y. In a sense, we're looking at the graph dy by dt against the y-axis, but we put the y-axis horizontally. All right, if you don't think like this, if you think this is a solution, then you'll be mentally taking the derivative and you'll end up with all the signs wrong. All right, so I'll show you this, but like I say, it takes some adjustment in thinking. Okay, so when you graph dy by dt, the equilibrium values, they're the values for dy by dt equals 0. So on the graph, these are equilibrium values. On the graph, it would be where the curve dy by dt crosses the horizontal axis. So instead of solving for it, you pick them out graphically, numerically. Right. Then you look at the curve. If the curve is above the axis, then draw the phase arrows up. If the curve is below the axis, the arrows are drawn down on the phase line. Again, this is sort of a confusion because if you look at that curve approaching the equilibrium or moving away from it, then you kind of get in trouble. So just follow these rules. Graph dy by dt against y. Where it crosses the horizontal axis, right, crosses the axis, those are the equilibrium values. The curve above, if the curve is above it in that region, then draw the arrow up. If the curve is below it in the region, draw the arrow down. And here I'll show you an example now. Okay, I've got all this on one slide, which, sorry, it's not in there in a very nice manner, but I hope you can see everything here. This is the derivative. So here's my differential equation. Oh, brilliant. Those should be y's. I'm sorry. Let me fix it. Okay, so here is the differential equation. This is dy by dt, and you can see right away that it is autonomous because there is no t in this equation. Dy by dt is only a function of y. Okay, so it's autonomous, and we can write a phase line for that because all the isoclines are going to be horizontal lines, and we can condense all that information over into the phase line. So in this case, if you want to find the equilibrium solutions, you have to set this equal to 0. Obviously, you're not going to find this by an analytic means. So you can graph it. And this is a graph. This is a graph of dy by dt, this equation, as y changes. That's why I kind of emphasize this down here. These are just numerical values of y along this axis. Maybe you don't have as much problem as I do adjusting thinking to some of these situations, but I just point this out for those of you who do. This is a graph of the derivative. It's a graph of this f. Right. Where it crosses the y-axis, where it crosses this horizontal axis, are the equilibrium values. There's one right here. Okay, and I mark that here. There's one here. You have to find this numerically from the code that you use to graph this. Yeah. And this one's here. This one's a little over 3, and it's right here, and there's another one at 5. So these are the roots of this polynomial. There's 6 roots. They're not duplicated. There's no multiplicity in the roots. And in this case, just for demonstration purposes, here we have them all. So these are all those roots are the equilibrium values, and we found them by graphing it and picking off the points where the graph crosses the horizontal, the y-axis. So we graph this against y. Right. Now I marked in red here all of the regions where dy by dt is greater than 0. When it's greater than 0, you draw the arrow up. So let me try to show that. Alright, so in the region less than, I guess this is the y values that are less than this lowest equilibrium, the curve is above the axis, so the arrow here is up. Now if I move to the region between these two equilibrium values, it's down. I'll leave that for a minute. Now between this equilibrium value and this equilibrium value, that would be between here and here, the curve is up. Again, don't think of it as approaching this node or approaching that node. Just think, is it above the axis? It's above the axis, so I have to draw the arrow up. And continuing between these two, That would be between here and here. The curve is up, so I draw the arrow up. And then the last one is also up. The others are pointing down. Let me try to say that again. If the curve is above the axis in that region, throughout that region, you draw the arrow up. Don't look at the node and think of the curve approaching the node and then taking a derivative. We'll do that in a minute. Just look at it as though it's pointing, it's either above the axis or below the axis, and then you draw in the arrows and you're done. So actually that's pretty, if you can adjust your thinking and get that idea in your head, that's a pretty quick way to draw the phase diagram, the phase line. And now we can look through the phase line and see which ones are stable or unstable. We're looking at this node and we see the arrows are both moving away from it. It's unstable. For this node, the arrows are moving towards it, both pointing towards it. It's stable. Here they're moving away, so it's unstable. Pointing towards it, stable, unstable, and stable. Now we'll look at the third method. This method I'm calling the next derivative test. All right, what I mean by that is that we have the differential equation dy by dt, and it equals some function of y because we're dealing with these autonomous equations. Right. I'm going to take the derivative of this. It's really not the partial because it's only a function of y, but it could be y and t, so I'm write it as partial. Oh no, I did write it as, okay. All right, I'll follow what I did earlier. I'm going to take the derivative with respect to y. That means taking the derivative here with respect to y. Right, and I'm going to evaluate this at the equilibrium points. Again, it's the next derivative because I'm taking the derivative of the derivative, but I'm taking it with respect to y. In the book, it's sometimes written as y prime, sometimes he has some h primes and means the same thing. So you have to do some careful reading there when it's being discussed in the book. Remember that in that file called homework, suggested homework file on Blackboard, I put the pages in the text that correspond to the topic that I'm discussing in this lecture, because the textbook talks about things in different places, not all in one place. And so I'm talking about things all in one place, so I have to refer to the different sections of the textbook. So let's go back to the graph of dy by dt, this graph right here, and figure out what this means. What we're looking at is taking the derivative and evaluating it. Now here's a previous picture for the previous test. Let's look at, we'll look at these in a more blown up version, but here's the idea. The arrow was up here, okay, well let's look at this one up here. The arrow was up here, so we drew, the curve was above the x-axis here, so we drew the arrow up. The curve is below the x-axis here, we draw the arrow down, and we say that's unstable. But if you look right here, in order for it to go from below the x-axis, or the y-axis being the horizontal, I'll just say from below the horizontal axis to above the horizontal axis, the slope right through here has to be positive. This slope is that next derivative. Right, so the slope is positive at an unstable node. Here's a stable one. In order to get from a plus to a minus, the slope, again this slope, this derivative has to be negative. So now that's the basic idea. We'll look at this in a little more detail. Well, first here's a summary. If you take that derivative, that next derivative, the derivative with respect to y of dy by dt, and you evaluate it at an equilibrium and the result is positive, that equilibrium is unstable because that curve is crossing from, here's your y, below the y-axis to above the y-axis, so that's a positive slope. If it's negative, then the equilibrium is stable, and if it's zero, then the method can't classify the equilibrium because it's semi-stable. You have a situation like this, or like this. And this is just an expanded view of the graph from the previous method. And we'll just go over it again so that you absolutely have it and never have to think about it again. Here we have an equilibrium value right here. I'll draw a phase line for it here. And here's that equilibrium value. I just wrote it over there. It's like minus 3.9 or something like that. And it's an equilibrium value. This is dy by dt. It's above the x-axis here, or I'm sorry, above the horizontal axis here. The horizontal axis is actually y. So that arrow is positive. Now, it's not like you take this region is really the region here. This region is really the region over here. Again, like I said, it requires some adjustment and thinking. This is above the x-axis, so in this region I draw an up arrow. This is below the x-axis, so I draw a down arrow. This is a stable stable equilibrium. Okay. Now if I take the slope through here, the slope is negative, and that's another way to find out. Instead of looking at what's above and below, I could just look at the slope right through here. So I'm going to repeat the procedure here. Here's going to be my phase line. I have an equilibrium value here, which is about minus 2.2, we'll say. Okay. All right, the region preceding this this is positive, okay, it's a negative value, so this is going to be an up arrow here. This is going to be a down arrow here. It's unstable. If I look at the slope right through here marked in blue, it's a positive slope, and that's another way to find it out. And here are two examples of semi-stable equilibrium values. Now we'll do an example. We'll use the same modified logistics equation that we used in the first example when we just drew phase lines. And we found, as before, that there were three equilibrium values: 0, m, and n. Remember that m is less than n. And all the values are greater than 0. Now we take the derivative of this with respect to y. So what's the advantage here? We don't have to graph this. We just take its derivative. And now if we did the first method, we'd have to find little points in these regions between here and evaluate the derivative. But in this case, we're just going to take the derivative with respect to y and evaluate it. We'll evaluate it first at y equals 0, then at y equals m, and then y equals n. Okay, so here's the derivative evaluated at y equals 0. It turns out to be negative. If it's negative, then the stability of the equilibrium is stable. Here we evaluated at m, remembering that m is less than n. Here's what we get here. It turns out to be positive, so this is an unstable node. And now we evaluated at n, find out it's negative, so it's stable. So that's, those are the three tests. So let's summarize what happened. We have the direction field with the isoclines, particularly the nullclines, drawn for the autonomous first order differential equation. Some function of y only. All of these are horizontal lines. Now the equilibrium solutions, the nullclines are also solutions. They are the equilibrium solutions of the equation. Now the regions between and above and below the nullclines, or these equilibrium solutions, the flow is similar. If the tangent's up in one of those regions, all the tangents are up throughout that region. Or if the tangents are in the negative direction in a region, one tangent is, they're all negative in that region. There is no change in t as you go across it because it's autonomous. Therefore, why draw the whole thing? You can summarize all of it in the phase line. In the phase line, you put the equilibrium values as dots, and you represent the positive slope with an up arrow and the negative slope with a down arrow. So the next thing we talked about was the stability of the equilibriums. Equilibrium values can have three kinds of stability right now. It can be stable, which is called a sink. It can be unstable, which is also called a source, or it can be called semi-stable. Right, and there's three ways to pick that off. The idea of a stable situation is that if you move a little bit off of it, you're going to come right back to it, even asymptotically. An unstable situation, if you're on that equilibrium value and you move off of it, you're going to fly away and not come back. And semi-stable, it depends on what direction you move. So when you look at the phase line, if those arrows are pointing away, that tells you what is going to happen to you if you move off that equilibrium. You're going to fly away. So this one is unstable. Now, in this case, the arrows are pointing toward it, right? So if you move a little bit away, the arrows are going to bring you back, even asymptotically. So this is called stable. And there were three methods to find that. One, just look at the phase line by picking out points. The second is to graph dy by dt as a function of y. Watch where it crosses the y-axis, which is the horizontal axis then, and then look at whether the curve is above or below. There's a little bit of adjustment and thinking on that. In fact, I find that one fairly difficult. The next is to take one more derivative, take the derivative of this with respect to y, evaluate it at equilibrium points. If it's positive, the slope through there is positive, it's unstable. If the slope through there is negative, it's stable. If it's zero, it's semi-stable. We're going to see a lot. We're going to see this idea of stable and semi-stable equilibriums throughout the rest of the course.